Hi, today we're talking about shear. So shear is when an internal load, which is to say, of course, it's stress, are applied across or parallel to a cross-section. Remember, axial load was normal or perpendicular to the cross-section. So this is easy to see in pins, bolts, nails, those types of structures that I have showing on the slide right now. When I'm looking for an example of this, sort of in common culture, I kind of think of, the pictures of a strongman, it's kind of Superman in the comics growing up, where he's pulling a chain apart. That would be an example of the normal stress or normal load. Of course, the other one was to tear the telephone book apart. That would be an example of a shear stress because it's going parallel to the face of tearing. And it's not lost on me at all that this example is probably somewhat dated, as they're not really producing telephone books anymore, and who would want to tear apart a Kindle? So yeah, I know I got to work on that, but anyway, we're back to shear stresses. It's one face sliding over the other, or internal forces or internal stresses acting parallel to the cross section. So direct shear stress. So in the example, we can see the middle section is trying to slide as a rigid body into the space below it, sort of on the plane BD. And it has two shearing faces that are resisting that. So that's the face represented by AB and the line CD. And you can kind of see the deformations in the image drawn there. So let's isolate that middle section and see it. So if we apply equilibrium to that middle section, we see that along those two shearing faces, we must have internal forces to resist the load F pushing down on the bar itself. And we denote these by the letter V, which we use commonly to refer to a shear force. Now, you and I both know, because we were paying attention when we were talking about axial loads, that an internal force is simply a manifestation, mathematical manifestation of the stresses that are causing it. So let's have a closer look at this piece, and specifically the face, because that V is actually a series of shear stress occurring across the face. Now, like in normal stresses, we know that there can be high and low and everything else, but we're really talking about the average stress. And so we can calculate the average shear stress. And for shear stress, we use the Greek letter tau. So the average shear stress is equal to that shear force, V, divided by the area of the shear plane, A. When you're talking about stress in the axial load section, we referred to the fact, or mentioned the fact, that stress occurs at a point. It's probably time to start looking at that point. So to represent a point, what we use is a differential element, and it's a small, infinitesimally small cube, oriented as per the axes that we've defined. And on it, we can represent the stresses that occur at that point. So in this case, we have a differential element, and on it we have shown our shear stress, denoted by tau. Now, the one thing that we do know is that for equilibrium of this differential element, that shear stress must be represented not just on the face that we're looking at, but on the other four in-plane faces as well. And we're going to look at that in just a second. Okay, so here we see our differential element once again, and on it, slightly darker, I have drawn in our shear plane that we're interested in. On it, we see the shear stress that we calculated or are looking at, tau yz. So just a quick comment about the nomenclature of the subscripts. So in this case, we're using the first subscript refers to the plane on which it's occurring. In this case, it's a plane that is perpendicular to the y-axis, so it gets a y, and the z is the direction of the shear stress. It would go either in the x or the z direction in this case the z direction. So we have tau yz. So equilibrium shows us that tau must be the same for all in-plane shear stresses. So by in-plane shear stresses, I'm talking about those other three shear stresses that occur in the same plane as the one that we just drew in. And here they are shown here with their various nomenclatures. So if we apply equilibrium, let's do our sum of the forces in the y direction and set it equal to 0. So if we look at our forces occurring in that y direction, so we have the top plane, or tau zy, and we have the bottom one, tau prime zy. To get those stresses into a force, they must be multiplied by their area. In this case, that is the area of the plane of the differential element, or delta x, delta y in this case. And we set those equal to 0. And what we can see is that those two shear stresses must be equal to each other. If we do sum of the forces in the z direction equal to 0, we can see the same thing for our two vertical shear stresses, tau prime yz and tau yz. And then finally, when we do sum of the moments, we do sum of the moments about the x-axis in this case, and we set it equal to 0. So the two negative face shear stresses, they disappear because their perpendicular distance to the x-axis equals 0 because they go through it. So we only have the two. We have tau zy and we have tau yz. We turn those into forces by multiplying through by their areas, and then their moment arm is that length of the side of the differential element, so delta z and delta y. We set it equal to 0, and what that tells us is that these two pairs now are also equal to each other. Thus, all four of the in-plane shear stresses are equal to each other, and not only that, they are also pointed or oriented, as shown on this diagram, pointing towards opposite corners. So let's talk a little bit about direct shear, and we'll start off with something we refer to as single shear. Single shear, all that means is that there is a single shear plane that is resisting the loading. So this is a fairly common joint that you might see, particularly in woodworking or something like that. It's called a lap joint. Two boards coming together, there's a glue line between them, and that glue line is designed to resist the shear force. And we know that by using our free body diagram method of sections. We can cut along the glue line as our method of sections and realize that there must be a shear force on either side of that shear face and equal to and opposite to the force in the section, or V would be equal to P. Another example of a single shear construction would be if we were to bolt those plates together. In this case, likely the plates are made of some metal, and then isolate it and break it, and we see that there is a shear force resisted by the bolt. Now, it was fairly obvious in the glue line to see that that glue line covered the entire area where the two boards came together. In the bolt, if we look very closely, we see it is the cross-sectional area of the bolt itself that is resisting the shear force in this case. So let's look at it a little bit closer just so we can completely see what exactly that shear area is for a bolted connection. So we've done it up in 3 dimensions, and we have that same connection here. And what I want to do is I want to remove the top plate and the top half of the bolt so we can see just the bottom blue portion on the screen. And so I show it up here, and I apply my my static equilibrium in order to determine that the shear force, which we know must be occurring in the bolt, being to transfer it from one plate to the next plate, must be equal to P, or V is equal to P. But how is that carried? Let's isolate on the bolt itself. So let's look at the bolt and isolate on it. So the first thing we see is that P must be applied to that bolt, and it's applied to it where the blue plate kind of wraps around the bolt itself. And then that has to be resisted by the shear force, which is resisted through the cross-section of the bolt. Let's make that a little bit bigger, because we know that that shear force actually has to be a manifestation of shear stress. And so we can replace it with a tau. And in this way, we can very clearly see what is the cross-sectional area that we're talking about when it comes to the resistance of the shear resistance of the bolt. And if we apply our equations, in this case, we know that tau is equal to V over A, but we have demonstrated that V is equal to P, and we can get that our shear stress caused in the bolt in this case is equal to our force P divided by the area, and we can clearly see that the area that we're talking about is the cross-sectional area of the bolt. So we've done up an example. It's available at the link shown below. It's a fairly simple, straightforward example, but I do recommend that you follow the link and go through it in slow time and make sure that if you have any questions whatsoever that they're answered before moving forward. It is a fairly common mistake for students to misidentify the area of the shear plane. So we've talked about single shear. Let's talk a little bit about double shear. So like in single shear, which referred to a single shear plane to resist the loading, double shear is pretty much means the same thing. It's two planes, two shear planes to resist the loading on the bolt or the pin or whatever it is that's carrying it. So in this case, we have a structure. Think of it as a turnbuckle or some other saddle rod type connection. And we're going to idealize that, break it apart, and look and see what's going on inside. So here it is idealized. We have a load P on either end, and we can see where that rod or bolt, which is going to resist the shear forces, would pass through it. So I'm going to do my free body diagram here and apply my method of sections. Now, a little quirky in this case because we've always drawn our method of sections as a straight line plane, but there's no requirement for it to be a straight line. So I'm just going to pass it through here so to divide the bolt in an obvious place, separate these two things. Now, I'm still showing both of them. Keep in mind that we would typically, with the method of sections, throw away the left side, throw away the right side. You only need to really look at one of them. And we can see where the shear planes are, and the internal shear forces V must exist in order to maintain equilibrium in those two partial free body diagrams that we now have on the screen. In applying our equation of static equilibrium, we can also look at this and see that our individual shear forces V must be equal to half the load, because it's double shear. There are two planes for every P that's out there, and so we get half the P. So a physical representation of what we just kind of looked at, only in this case we have a different configuration where we have two plates bolted to a single plate. This also is a fairly common configuration in the construction world, preferable to the kind of lap joint type construction we saw before, because in this case the uniaxial forces are always symmetric about the longitudinal axis, whereas that wasn't always the case before, which has some issues which we can talk about. So what we're going to do is we're going to do this in steps. Let's take away the blue plate and see what we look at. And so here we see it. We've taken away the blue plate. We can see the two shear planes. It's a single shear plane of resistance, but there's two areas, if you will, associated with that. And each of those areas would have 1/4 of P in addition to the P over 2 still in the blue plate to resist the applied force P on the green plate. So if we remove the bottom blue plate, and you can imagine the cut planes of the bolts underneath, we have P over 4 in each of those. So in this case, it's really been just a double shear case, but we happen to have 2 bolts. So 2 bolts and 2 planes on each bolt for double shear, and we get 4 areas that are resisting the shear. So each one is carrying P over 4. This kind of demonstrates one other choice that you might have as a designer if you were designing a connection like this. We've talked about sizing the bolt, making sure it's large enough or strong enough, the right material to resist the shear forces. But you can also choose to make a choice that there are enough of them. Can we increase the number of bolts? You have to have enough area in the joint in order to accommodate the bolts. But that's another choice that the designer has available to them when looking at shear connections, bolted shear connections. So we've done up another sample problem, and I've given the link to that sample problem here. It's a double shear problem. In this case, we decided to look at a weld, and I invite you to follow that link and go ahead and look at the problem. And I won't talk about it too much here because it's fairly well explained in the link itself. So we've been talking about shear stress, but we should probably talk a little bit about shear strain before we go. So as we know, shear or stresses will cause strains. So your deformation that is a result of the stress is referred to as the strain. And so we have our differential element and we have our shear stress applied to it. We denote it as tau. Remember that tau is equal on all 4 of those faces pointing to opposite corners. So we only have to know one magnitude because they're all of the same magnitude. And so we show it as a single tau. So if you imagine what that little differential element would look like, if you think of a small sponge and you grip it on the 4 faces where the shear stress is and you squish it, you will see that this is very similar to squishing it by the opposite, or pulling it apart by the opposite corners where the shear stresses are pointing at, and you would probably get a shape, a deformed shape looking something like this. So our nice little square differential element is starting to look like a little bit of a diamond from this direction. The shear strain then is the change in the angle that represents that shape, and we see we use gamma, Greek letter gamma, divided by 2 in this case, because half of it would be between the y-axis and the diamond shape, and half of it would be the x-axis and the diamond shape itself. Now, we don't normally leave it like that. We idealize it, simplify it a little bit, and what we're going to do is combine those to a single shear stress gamma, shown here on our idealized shear strain diagram. So one thing you should know is that the relationship between shear stress and shear strain, very similar to our relationship between normal stress and normal strain, is that tau is equal to G gamma, where G is our shear modulus, analogous to the Young's modulus in the axial case. So this relationship is referred to as Hooke's law for shear. It's, as we said, pretty much identical to what we get for Hooke's law for axial load or normal stresses, normal strains. G is the shear modulus, which is the slope of the shear stress, shear strain curve, and can be seen here. Now, one thing we need to nail down so that we can talk the same language is what are we going to refer to as positive and what are we going to refer to as negative? What is our sign convention when it comes to shear? It's a little bit more complicated because, as we saw, it's existing on all 4 of these faces, and what does that really mean to us? And so we have to have a way of coming up with a sign convention where all 4 of those will have the same sign but reflect the directions that they're pointing in. And so we have to look at 2 things. We have to look at the face that they're on, and we have to look at the direction they're going in. And much like multiplication in mathematics, if we have 2 negatives, they will multiply to be a positive. If we have a positive and a negative come together, they will be a negative. If we have 2 positives come together, it'll be a positive. So a positive face, so if I show on this diagram, I'm showing the positive faces and the negative faces, and their derived based on the axes, right? So if you're on the positive y face, you're at the top. If you're on the negative y face, you're at the bottom. Positive x face, you're on the right. Negative x face, you're over to the left. And so those are shown here in the diagram. And we put those through together with the direction that they're pointing. And so I'm showing the positive directions there and the negative directions here. And so between all of that, we're able to define for a given shear stress whether it is a positive shear stress or a negative shear stress. This is something that you probably want to practice a little bit and pay very close attention to it when you're going through your problems, because it is an area of confusion and common mistakes when starting out doing some of these problems. And one thing to note is that the shear modulus, which we just looked at, is defined by Young's modulus and Poisson's ratio, nu. And so the three of them are all interrelated. So if you know any two of them, you understand or you know the other property as well. They're all completely related. And so often a problem might give you just Young's modulus E and your Poisson's ratio, and you would then be expected to understand that you have been given, tacitly given, the shear modulus. You just have to take a step to calculate it.